view of the assignments and the kind of formats you people are using. This is Excel sheet, which is from the submission form. And I'm going to open some of them and try to discuss exactly what is missing and how to basically. So let's see, this is Akash. There is no name and roll number. So the document, first of all, should have name and roll number on the very first page. And it should be assignment wise, assignment 1, 2, and so on. And here, this is only, I guess, yeah, this is the first assignment. And it will be good to basically copy paste whatever assignment I have given. The statement also should be copy pasted. So first thing is the problem statement is missing. Circuit snapshot is given, which is okay. And then it will be good to mark the W by L also. So once you take the snapshot in the PPT, you can also place the W by L values. You can take it to PPT or paintbrush and you can mark the W by L values. That is generally helpful. And then the characteristic sweep has been given, which is yeah. So and then for different values of WP and WN, rise time, fall time, trying to find out. So WP, WN change and rise time, fall time, you're trying to find out. Okay, so which is okay in this case. You could have made a table also, rather than putting like this, you could have made a table, rise time, fall time, W by L. So here we see the W1 micro, 0.4 micro, you are getting certain fall time, rise time. Fall time is 1 microsecond. How is it 1 microsecond? Something is wrong. 1 micro. I think there is, I'm not sure which MOSFET model he's using because such a big, I don't even see any transient. So where is the transient waveform? And from where this 1 microsecond is coming, I have no idea. So something is wrong the way the data is reported here, because I don't see any transient simulation. I don't see any how the rise time, fall time has been calculated, nothing. So this is wrong. Something is wrong. So while calculating this rise time, fall time, it is expected that you post the transient plots and show how the rise time, fall time is calculated. Like use a marker, try to show the 2 points, like how the rise time, fall time are coming. Are you people able to place 2 markers? Have you seen whether you are able to place 2 markers at 2 points?
Yes, sir. 2 cursors we can place.
Yes, so in the same snapshot, you can place 2 markers so that some people have taken separate snapshot for the upper point and the lower point of the rising edge, which is again not necessary. It makes the report clumsy. So in the same waveform, you can place the markers at 2 points, the rising point and basically the rule of rise time, fall time calculation is generally 10% to 90%. So 10% of the waveform, that means in this case, if you are 10% of the range, basically. So in this case, if the VDD is 1 volt, 10% of that is 0.1 volt. So 0.1 volt to 90% of the range. That means 0.9 volt. So 0.1 volt to 0.9 volt, whatever the time it takes to transition, that will be the rise time. And likewise, on the opposite side, from 0.9 volt to 0.1 volt, the time it takes to transition will be the fall time. So you can place the markers in the same waveform at these 2 locations, and then it is clear that okay, how the rise time, fall time has been calculated. So here, the way it is calculated, it seems like okay, the way okay. So he is getting 0.8 nanosecond. All right. So cap value also I'm not very sure because he has not mentioned what is the. I don't think there is any cap attached, but still 0.8 nanosecond, it looks like on the higher side. And in both cases, he is not showing any significant effect on the rise time, fall time. All cases, it is coming similar only, which is a little surprising. I would expect significant change because of the W by L changes. And the condition for the circuit, I hope there is no capacitor also, but still I would expect significant change because of the. So what is your observation? Other people also get similar value? Anybody else? You got similar value of rise time, fall time, almost similar. Because here all these W by L changes that he has done, I'm not seeing any significant effect. So all cases it is 0.8, 0.9, 0.8, 0.9, something like that. And it will be basically important to show the calculation using the waveform. So I will see some other reports also. And then this circuit has been shown, and task 3, I don't know, task 1, task 2, and task 3. Voltage source on the NMOS gate, reverse polarity. So here I think the task 2 is also not complete. There was some question regarding how to basically which combination gives you the worst case rise time, fall time. Those things has not been done. So this is not complete, it seems. Part 3, we had added another voltage in gate of M1 and M2. So in this case, it seems like V1 0.5 volt, which is very high. I don't know how he has added 0.5 volt. This is also not apparently correct. So the transition point, if you look at this V output, it is shifting by a big amount because he has added a big voltage. So this is, I had mentioned something around 50 millivolt. He has added 0.5 volt. So even this waveform is not correct. And then going ahead again, same thing, he has done 0.5 volts. So that is shifted the curve towards extreme right. So plus minus. So yeah, things are not complete. Here also we had asked for worst case scenario for 2 inverters in series. So that has not been done. Let me look at some other assignments. Some people had made it very clumsy. That's what I. Now this is Ahwaban. This is a pretty complicated name. How do you pronounce it? Ahwaban. What is he present? I don't know. So VTC, this is the first question. I asked everybody to keep the first assignment also, but I'm seeing that mostly people have put only second assignment. So in the same document, first assignment should also be put. So here he has calculated the rise time, fall time. First case he is getting 23 micro, 23 pico, 21 pico, which is reasonable. This is a range I would expect. Here the other previous one, I think it was wrong. And again, it will be good to show the calculation also. Here, the calculation is not shown using the waveform, so showing the waveform will be useful. And then for 2 micro VTC, there is some reduction in the as compared to the previous value. The rise time has increased slightly, not much, but slight increase is there. And that is here because the PMOS strength is similar. PMOS strength we have not changed. No, PMOS strength is increased and NMOS strength is also increased. 2 micro by 2 micro. Is this what I asked? 2 micro by 2 micro. 1 micro by 0.5, 0.4 micro. And here both the devices have been increased. And the 1 micro by 1 micro. I think these numbers are not correct. So I did not ask 2 micro by 2 micro, 1 micro by 1 micro. These numbers are not correct.
Sir,
So
third one was 1 micro by 1 micro. Second one was 2 micro by 0.4 micro.
yes, but those values are not here. So he has done something else. So 1 micro by 1 micro, the ratio is remaining same and device dimensions are bigger. It will improve the rise time, fall time both to some extent. In this case, it seems like not much improvement, only similar values are coming. And in case of 2 micro, similar values. And in case of, in this case is 1 and 0.5, 0.4 micro. Here also not much change. So all these are coming very close, 25, 21, 24, 20. And in this one, it is 1.4. So even then, it's not much of a change. And that may be because of the input rise time, fall time being, what is the input rise time, fall time? 50 picosecond you had used, right? What is the input rise time fall time you have used? You people have used?
Sir, 50 picos.
That is having some effect, and it seems like the device's contribution to the rise time fall time is not very significant. That means, and that's why it is coming very similar in all these cases. If we simulate with the ideal
5 picoseconds.
if we simulate with very sharp pulses, then it will show some more significant effect on the output rise time fall time. Right now, because of the uh, devices being faster and the rise time fall time of the input being significant, 50 picosecond, the contribution of the devices to the rise time fall time is not much. It is not degrading the rise time fall time much. So that's why actually it is not having much of a effect. If you put some load capacitor, then it will start having more pronounced effect because of the sizing. Right now, the devices are fast enough and they are actually improving the rise time fall time as compared to the input waveform. That's why we are not seeing much effect. So there are two cases: either you put some cap and then the device will get loaded, and then the rise time fall time will become more strongly dependent upon the output. So if the rise time fall time contribution, or basically the rise delay, falling delay of the inverter is faster than the input rise time fall time, then it will not show much effect. That's what is happening. So in this case, you have simulated with input rise time fall time of 50 picosecond, but the devices themselves are seeing transitioning faster. As a result, they are not contributing much. The output waveform is not very sensitive to the rise time fall time. That's what it seems like is happening. So anybody who has simulated with smaller rise time fall time, they say 5 picosecond kind of rise time fall time?
Yes, sir. I have done with 5.
Yeah, so I will go to your report and then let us. So tell me, what is your name?
Sir, Sutanu Singh.
Sorry?
Sir, Sutanu Singh. SUTANU.
Your voice is not coming clear. SUVA?
SUTANU. Sir,
I'm
T,
not able
sir.
to hear clearly. Can you clearly speak? I think some audio problem.
Sir, SUTANU.
SUBA.
T. Sir, can you hear me, sir? SUTANU.
Sutanu Singh.
Yes, sir. This one, sir. Yes.
Okay, so here, all right, so VDD and length is initially 45 nano, 0.25 micro, 45 nano, 0.125 micro. And here rise time fall time is again 50 picosecond. You said you are simulating with 5 picosecond.
Sir, this is the first assignment which you sent. In the second assignment, I did.
Okay, so let us go to the second. Second assignment is this W and WP, and rise time fall time is this much. And here transient waveform you have also not plotted, but here you are seeing for 0.4, this was first one is 0.4 and 2. Second one is for 0.4 and 1, 1.4. Generally, W by L we write first, 2.4 and 1.4. So if you have 1.4, that means the rise time should be degrading a bit. But again, we don't see much degradation in the rise time, because as compared to the earlier case, W is 2 micro, here W is reduced to 1 micro, but we are not getting much change. In fact, the rise time has improved. So we are not seeing much degradation. And that may be because, again, the devices are faster. The input rise time fall time mentioned here is.
So one thing that here it may show that 50 pico may show in the circuit diagram because I forgot to change. No, sir, actually this is not the one. It's the second part. You're seeing the assignment to the first part. There's assignment to second part. This is assignment to part 1. It's an assignment to part 2.
This is the waveform, right? So this is the rise time fall time for different W.
So this is the assignment one, part one, which you discussed. This is not the duty cycle one. That is the series inverter one, which you mentioned in the second part. Yeah, this.
Where is
Yes.
where is the second assignment starting from? Starting from here, right?
Yeah, it's starting from here. In the first one, second assignment, I have used a normal waveform of 50 picosecond rise time fall time. In the second one, where you use the duty cycle one, there I've used a 5 picosecond, 5 picosecond rise time fall time. Because in that one, the duty cycle was not coming much different. If
That
I
is
use
understood. So
50
that you have to adjust. So if you give a rise time fall time, then it will subtract from either the on period or the off period.
yes.
So now if you see here also we are not seeing much effect. So what I was expecting is that if you change one of them, say in this case WP has been reduced to 1 micro from 2 micro, but rise time fall time is remaining almost similar. Not much change. Fall time has improved actually. Rise time also slightly improved only. And then W and WP both 1 micro, again similar, not much effect. So and here you have few of them. So the delay point of view, some improvement, some changes are happening. This is again transient simulation. So in the transient simulation, of course, the characteristics is shifting as per expected, right? Characteristics shift is as per expectation. Because in this one, we don't know which one is which one. So you should at least mark.
Yeah, I've written sir, because I was not getting the option how to mark LT spells.
That you can take it in the PPT and you can put some text over it. That's how we do it. If you have to edit any figure, you can just put it in the PPT, take the snapshot, keep it in the PPT, and add some, annotation, put some text over there, and then put it here. Even in Word, you may have, right now in the Word also you may have option for editing, but the best way is to put it in the PPT. So change in the duty cycle. So here, the issue that I'm seeing is that we don't see much effect in the rise time fall time. There is some effect. I'm not sure how accurately it is calculated and whether you have taken enough number of. In the waveform also, it is clear that it is not changing much. The rise time fall time is not changing much. So maybe if you put a cap, then it will show some significant effect. As of now, it is not changing much. Expected behavior is that if you have bigger NMOS, the fall time should improve. Weaker PMOS, you're reducing the PMOS dimension, rise time should degrade. That means rise time should increase. So that is remaining close only. And then so in this case, what is expected is that if you have the opposite scenario, that means first inverter WP is higher, WN is smaller, second inverter just the reverse. That will give you the worst scenario. So is that something you have observed?
Yes, sir, that was the one. In the first case, I have put the WP highest, WN lowest. And the second case, I have put the WP lowest given and the WN highest given. That gave me the worst delay, like worst change in duty cycle.
But the way you have shown the diagram, we can't even calculate the duty cycle because you should show at least one period, right? So you have shown only half the period. The transient waveform, you have shown only half the period. So here you should show the full period at least. So here, if we are looking at the worst case, stage 1, WP2 and 0.4, W1, stage 2 is this. Stage 1, stage 2. Too many combinations, I think A and B. So I had given only 2 combinations to be tested, right? So not all 4. So W2 and 0.4, 1 and 0.4. 1 and 0.4. So the worst case scenario will be when in first inverter PMOS is strong, NMOS is weak. Second inverter, it is just the reverse. Because first case, if that happens, then the first device will have a good rise time. It will charge fast. And the second one, again, you have a basically strong NMOS, it will discharge fast. So that will basically lead to reduction in the duty cycle. And then BTC of inverter with different threshold voltages. Here, the VT that you have chosen is how much? The V1 is how much? V1 is 0.05. Okay, so V1 positive, you will get a shift. I don't know what is what. So again, without marker, we can't assess what is what. So in all these kind of waveforms, please make sure that you are putting some marker. Marker means either you take it in the PPT and put some text on it, and then take the snapshot and come put it in the document. So I can show you just a quick example. Either paintbrush or PPT works. So I can take any snapshot. Suppose this one. And generally, it is good to save the pictures in a proper ratio. So here, once you have this, you can put a marker, insert text, whatever, this is case one, whatever, case one, or you have to put the numbers. So delta VT, delta equal to plus 50 millivolt case. Which one is nominal, which one is, so this is blue. And delta is equal to Z. So just small amount of annotation. Now here I have put the color coding. So color coding is such that I understand that this is, the green plot belongs to this case and the blue plot belongs to this case. And then I take the whole thing. I can group it also. And, I can paste this entire thing. In the document. So wherever, like if you have a Word document, you can go back. Or another, because here there is some formatting issue because here it is taking the text as it is. So first you need to convert it into the picture or JPEG. So one option is that you save it as the JPEG image, or a shorter option is that you go to Paint. You go to Paint, paste it here. Now it gets converted automatically into a bitmap format. Then you copy it and then you bring it to the Word. Now in this format, I can relate because it is properly annotated. So it doesn't take much time. You just take it to the PPT, put the annotation, copy paste it into the Paint, and then bring it here. And other option is that once you annotate it in the PPT, you can also uh, save it. So for example, if I want to save this annotated image, I can go back and where is the PPT? Let's show everything, not the PPT. So another option is that that is the more tedious option, I would say. So the shortcut that I showed, that is what I also use some many times. So here also you can save it, save as picture, then it will save the whole thing along with the text and annotation, everything as a particular picture, and then you insert that picture in the Word document. So quicker way is you just take it, copy paste into paintbrush. It will integrate everything, the text and the image, and then you put it directly in the Word. So that is common. There's a useful technique just to annotate and detail any picture, put any text, put any explanation, put any arrow mark or any indexes, and then bring it to the document. Going back to your the assignment. So this is something you need to do, and here anyway for different cases you have done it, which is expected. I hope you're getting it as per expectation. So inserting a positive voltage in the series with gate of NMOS will shift the curve towards the left and vice versa. With PMOS, it will shift it towards the right. So that part you should be careful. So this is okay. Now this part is well done, but the only thing is waveforms. I have told you some mistakes. Like in order to calculate the rise time fall time, you should show the 1 period waveform. Duty cycle, you show complete 1 period waveform rather than half. And some annotation should be done so that the diagrams are understandable. Which waveform is what is understandable. And I think that's it. And yeah, means one thing that I'm seeing in this report also, that the rise time fall time did not get affected much because of the change in WN and WP. As compared to theoretical expectation, it is not getting affected much. But other things like, as mentioned, the change in the duty cycle worst case scenario is coming as per expectation. So let me try to see one more assignment, any other assignment. Let's see. This is assignment 1. So right now, anyway, assignment 1 we already discussed. Assignment 2, the rise time fall time here is included in the snapshot itself directly. Okay. So horizontal, vertical, and the difference. So here 32 picosecond and 23 picosecond. So he's getting something around here. If you see, the calculation is visible in this one. In this window, he's showing the calculation and snapshot. So here it is 32 picosecond, and the second one it is 23 picosecond. Difference between cursor 1, cursor 2, and 32 and 24. And so W2 0.4, 0.2. Again, too many plots are not needed. Again, in transient waveform, in single plot also you can do it. But anyway, this is fine. He has shown the calculation also. So, and where is the value? So for W, so this case he's showing 0.024 and 0.0217. And here rise time has reduced a bit, and WP is 2 and 0.4. First case WP was 1 and 0.4. Second case WP is 2 and 0.4. And he has shown the rise time to be improved. So 0.024 and 24 picosecond from 32 picosecond. So that is expected. This is as per expectation, because increasing the PMOS will have improvement in the rise time. Fall time is remaining similar because again we have not changed. So here the fall time was initially 24 picosecond. Here it is slightly improving. It is becoming close to 22 picosecond, but major change is there in the rise time. And the second case WP, WN. WP is same as the first value. I think it was initially 1 micro only. So WP is same as 1 micro, but WN has been increased to 1 micro. So in this case, again, using the same method, you can see how the cursors have been used. Horizontal and vertical cursors have been used. Difference has been taken. And then the calculation has been shown in the window. So in this case, the fall time rise time has once again it is 0.026 only. Fall time is 0.024. So not much change. Fall time is remaining almost similar. Though here the NMOS size has been increased. So as compared to the previous case, the very first original case, where the NMOS size was only 0.4 micro and the rise time fall time was 0.024. Here also is getting almost exactly same rise time fall time, or basically the fall time is not improving much. And this is, so I think he has not covered all the cases, 3 cases were there. And then circuit diagram is given rise time, fall time, he has taken 20. So NMOS duty cycle is 25%. And I don't know, there is no, this is single inverter. And here there is no comparison of different cases. So I'm not sure what is this result. So I had asked to compare. He has just done it for one case and showing the rise, duty cycle. So again, this is not complete. And then second thing he has done is with the VT addition. So some characteristics changes, how the characteristics are shifting, observing that, which is okay. But again, the worst case scenario has not been compared. So the second part he has not done. So anyway, when I reviewed some of them, I give you some feedback, and based on that, you can improvise. So what we are seeing is some cases we are seeing that yes, there is some significant change in the rise time fall time, but in some other case, it is not changing much. And it may be because the devices are faster than expected. And this is again a predictive technology model, may not be very accurate. And the values are similar. Here also it is 20 picosecond kind of, in the previous report also 20 picosecond. First report that I saw, there it was pretty big rise time fall time, 200 picosecond kind of, which was little surprising. So that part, maybe we need to see how the calculation has been done. Any question for anybody? I will describe some part, like the worst case scenario I will describe briefly. So let me, just describe that part very quickly. So what is meant by the worst case scenario? So I think this one, the worst case scenario from both perspectives. In this case, if I look at it, suppose I look at the VT case, different VTs, same is applicable for the W by L case also. Ultimately, we are looking at strength, which PMOS is stronger, which NMOS is stronger. So you have two inverters in series. Both inverters are having different dimensions. So in first case, suppose VT of this nominal VT for all of them is suppose 0.4 volt. So nominal VT, VTN is equal to mod VTP equal to 0.4 volt. Just an assumption. Now, because of the process variation, because of the corners and process variation, random mismatch that we have discussed. So remember, the process variation will affect all the MOSFETs in a similar manner. Here, we are talking about random variation. So now in this case, what do I, so if the PMOS is, say, in first case, it is stronger. So that means the VT of this PMOS is going to be lower than expected, or let us say it is, weaker. So let us take the weaker case. So in the weaker case, the VT of this is going to be, say, 0.45, and this one is stronger than expected. So this is 0.35. And in the opposite, in this stage, there's the opposite is happening. This is 0.45 and this is 0.35. That means the VT is, in the first stage, VT of the PMOS is higher, VT of the NMOS is lower. Second stage, VT of the PMOS is lower, VT of the NMOS is higher. So what will happen if you have, say, the input diagram, input waveform. And now here we have the VT of the NMOS being high. So VT, VT of the NMOS being low. So what is expected? A lower VT means the curve for this one has shifted towards which direction? For the first inverter, if this was the nominal curve for the first inverter, how is that shifted? This is the inverter 1, this is the inverter 2. So for the first inverter, what is the scenario? First inverter, how will the characteristics shift? Are you audible?
So it shifts left.
Shift what?
So it shifts towards the left.
Shift towards left, right? Because NMOS is stronger. So this is the first and second case. You have NMOS VT is higher. That means NMOS is weaker, and PMOS is stronger. PMOS VT is smaller. This is VT. VT is smaller. That means PMOS is stronger. So now this will, the second case, it will shift towards this. So you have six are significantly shifted, right? So now if I look at any input waveform, so what will happen to that? So first case, the trip point is going to come earlier than expected. So let me draw a little bit more, rise time fall time. Let me give some more rise time fall time to the input signal. Now, suppose input side, how do we find out duty cycle? So from the midpoint. So from here, we will look at the, this is your T1 and this is your T2. So duty cycle will be something like the T on T1 upon T1 plus T2 into 100. That is the duty cycle. If I assume that it is 50% duty cycle, that means the T1, T2 durations are almost same. That is the ideal case. For clock waveform, we would like to have 50% duty cycle. Now, in this scenario, the first case, the inverter threshold has shifted a little bit downward. That means now the trip point is lower. So it will basically cross at an earlier point. So the waveform in this case will cross early, and therefore the transition point will come little early, right? The output waveform will fall down earlier than expected. And then at the rising edge, what will happen? Now PMOS is weaker, so it will take basically a lower voltage to pull it down. So once again, same thing, trip point is low. So now it will also rise at a later stage. So it will come like this. So you can see that this thing has broadened, right? So first stage, what will it lead to? It will lead to broadening of the low pulse. And the high pulse will become narrower. So now the high pulse, if you see, same thing will happen for the second stage. It will basically fall down earlier and rise. So this thing is becoming bigger. So the output waveform, which is red in color, after this is at the output of 1. So this is at output of 1. Now at this red waveform is the input to the second inverter. Now second inverter, what is the scenario? The NMOS is stronger, right? So the NMOS is weaker. The PMOS is stronger because the mod VT is lower than the nominal VT. And for the NMOS, the VT is higher than the nominal VT. So as a result, NMOS is weaker, PMOS is stronger. What will it do? Now, if the red waveform is the input to the second inverter, let me draw it separately so that we can draw it on the same waveform using another color. So let me use green for the second inverter output. Now, for the second inverter, your trip point has shifted upward, right? So the trip point is upward, and therefore we are going to have the input waveform. It will basically fall down at a much later stage, right? So here the output green one, so it will take a much higher voltage to make it fall down. So this, rather than this midpoint, expected ideal value is this midpoint, but now it will fall at a later point because the trip point is higher. Therefore, and likewise for the same thing for the red curve also, it will trip at a earlier point. So what you can see, this thing is going to degrade it further. Now this, the T on T off, the T2 dash T1 in this one is now T2, I would say T2 dash and T1 dash, or T2 double dash and T1 double dash, right? T1 double dash. And likewise, the red one was, let's say, red one was say T1 dash, or I would say call it T2 dash and T1 dash on period by off period. So you can see that if this is a scenario, it is having cumulative effect, right? So one phase is getting narrower, another phase is becoming bigger because of that arrangement of the MOSFET, because of that skewed arrangement of the MOSFET strength. In the first case, it is squeezing the high pulse, making it narrower. The high phase is being made narrower, and the second phase it is just doing the opposite. And as a result, the net waveform that you get at the output is going to be the most skewed version because their effects are cumulative. Means it is, if you had the opposite scenario, then it would probably cancel out some effect, right? Suppose the second scenario where you have, let me draw the second scenario. Second scenario means this is 0.5, 0.35, but your the VT of this one, VT of this one is also similar, the same, basically same fashion, 0.45, 0.35. So if this is the scenario, what will happen? So in this case, I can maybe draw the, I can take the first waveform, first output remains same. So I will just copy the red waveform as it is. It is already broadened. So I will take the red waveform, which is having slightly broader lower phase as compared to the higher phase, because the first stage effect remains same. What is the role of second stage now? Second stage, if I look at it, there also we have the same characteristics, but now the waveform is reversed, right? So the input waveform to the second phase is reversed. What is the effect of that? Now, once again, for the second stage in this scenario, the transfer characteristics is shifted downward. That means the trip point is low. So now for this case, if I draw the final output, the trip point is low. That means once again, it will try to climb up early. And once again, it will go down early. Again, it will climb up early because trip point is lower, right? This is a trip point lower. Again, it will climb up early. And it will go down early. That means it will have cancellation effect. So it will basically now it will, again get equated or basically become closed. Are you getting the point? So why the first scenario was worst case and second scenario is best case?
Yes, sir.
So if you're getting similar trends, because one thing that I'm seeing is in some cases in the simulations, you are not able to get much change in the rise time fall time despite changing the W by L. But is the trend for the duty cycle similar to what I explained just now for most of you?
Yes, sir.
Any question for anyone? So today less number of people have joined, 34, rest are celebrating Sunday. Anyway, so any question before we proceed towards the next topic? All right. So I think it will be better to stop this recording and again start afresh because otherwise the recording becomes too big. So I'll stop here and then again start. Anybody, any questions?